Hi, welcome back to educator.com. Today we're going to talk about sets, elements, and what they mean for numbers. So to start off, we're going to talk about the idea of sets, but a lot of courses don't address this stuff directly. You might find in the course that you're taking that your teacher never talks about this directly. These ideas build the foundation that the rest of math works on. So you can understand all the concepts that will come later in this course without ever having watched this lesson. But watching this first will help you see how it all fits together, which will really help your understanding, which will make it that much easier on you. Also, if you want to go on and take later more advanced math like calculus or even much more advanced college like abstract mathematics, this stuff is going to be really useful to have already ingrained in your mind. So these ideas are great down the road for you. So if you're going to take advanced math, really definitely watch this, get an understanding of what's going on. Once again, you don't really have to deeply understand any of these things, and we're just going to be touching it on the surface. But you want to get a glimpse of this sort of stuff so that later on you can really understand what's going on. And also it's just going to make things a lot smoother, especially when we're talking about functions, so you can get an abstract idea of how a function works, which will help you understand what's going on. All right, let's get started. A set is a collection of distinct objects. Each of the objects inside of a set is called an element. So example here, we've got two sets. 1, 2, 3 is a set. Each one of those elements is different than all the other elements, right? 1 is not 2 or 3, 2 is not 1 or 3, and 3 is not 1 or 2. Similarly for the set cat, dog, we've got cat different than dog, dog different than cat. Also, real quick, the way that we show that we're talking about a set, we're talking about objects inside of a set, is we've got these curly braces, and I'm not that great at making a curly brace, but it's something like that for the left side and something like that for the right side. You can see a nice typography typed out font brace in my slide here, but when I'm actually writing it out, I do something like these right here. So we put our elements inside of that, and we separate each of the elements with a comma. So that's just what's happening on a sort of like a type point of view. Okay. If we want to, we can also name these, right? We can decide, well, all right, I'll name 1, 2, 3, I'll name that set A. And if I want to, I can also name the set cat dog B. Because I might want to be able to talk about this, and instead of having to say 1, 2, 3 every time I want to talk about that set, I can just say A. The set A has such and such property, or the set B when it interacts with. That way I don't have to say cat dog, or if it was an even longer list like 10 or 50 objects, it would start to get really hard, practically impossible to say. So instead we can just change it to using a single letter or whatever symbol is convenient for our purposes. Furthermore, the order that the elements come in has no effect on the set itself. So the order that the elements appear in, that doesn't matter. We don't care about the order here. A equals 1, 2, 3, but that's the exact same thing as saying 3, 2, 1, and that's the exact same thing as saying 2, 1, 3, or any other way you have of ordering those things. The important part is the fact that it has all of those elements. The way that they come in, their places in line, that doesn't matter. It's just the group that you're considering, not the specific permutation of the line. All right, so that's the basic idea of a set. If we want to describe a set, there's a bunch of different ways to describe it. So here are pretty much the three most common ways that you're going to see. Directly saying all of the elements. So we could go through, and like I was talking about before with the curly braces and the comma, we just say each of the elements inside of the set. Ice, water, steam. Our set has 3 elements. We've just said each of the 3 elements. That's the most basic method. We just say what's inside of the set. Another way is we can clearly describe all of the members of the set. So we also might describe it without it being inside of the curly braces, but sometimes we'll actually leave it inside of the curly braces. The point of it is that we are able to go, oh yeah, that's everything that makes it up. So we could make a set out of the first 80 elements of the periodic table, so we would know that hydrogen would be in this set, helium would be in this set, lithium would be in this set, all sorts of different elements are going to be inside of this set up until the 80th element. 80th element would be in it, the 81st element would not be in it. So another way of describing it is to say what's inside of it. Here's what makes up my set, and there we go, we've got a set. Final way that we can do it is we can describe a quality or maybe qualities that each member of the set has in common. So the way that you want to parse this, the way you want to read this is X is saying this here is what our set is made up of. Our set is made up of all of the X, and then you read this guy, this vertical bar, you read that as saying such that. So all the x such that x is the first name of a teacher at educator.com would be this set. Another way of reading that vertical bar is the word where. X, where x is the first name of a teacher at educator.com. Anything will do here, so long as it's getting across the idea that this thing here in the second part is describing the quality required of the thing in the first part. So this part in the second part describes what happens over here in the first part. So for this set, if it's x such that x is the first name of a teacher at educator.com, then it's going to be a bunch of first names of all of the teachers who teach at educator.com. My name is Vincent. I'm teaching at educator.com since you're watching this right now. So that means that Vincent is inside of this set. There's going to be a bunch of other names. If you go and look at all the teachers, you'll see a whole bunch of different first names. But we know for sure that Vincent is one of the names inside of this set. Great. We can also symbolize stuff. If an element is contained in a set and we want to talk about an element being in that set, we've got a convenient symbol to show it. This symbol right here, element of, contained in. For example, if A is equal to the set A, B, C, then we know that A is contained in A. B is contained in A, C is contained in A, because they showed up right here in our description of what the set was. So we know that A is an element in it, and we use this symbol right here to show element of. We can also talk about the idea of subsets. If a set is contained inside of another set. If an entire set is contained in another set, and formally, as a formal definition, that means that every element in the first set is contained in the second set. So for every element we name in that first set, it shows up in the second set. That's how we're going to formally define it. But you can just think of it as it being inside of the other set. We're going to call it a subset because it's part of the other thing. It's like a subpart. So we call it a subset. The symbol for this is this guy right here, subset of. So if x is the set 3, and y is the set 1, 3, and z is the set 1, 2, 3, then x is a subset of y because 3 shows up inside of y. And then y is a subset of z because 1 and 3 both show up in z. So we are able to see, oh, that's a subset because everybody in here showed up in the other one. Furthermore, we know that this property has to be transitive because x is contained in y and y is contained in z. Then since x already lives inside of y, it must also be inside of z. If we were to see it as sort of a picture, we'd see it something like this. So x is contained in y is contained in z. So since z has y, it must also have x, so that we've got transitive property x is contained inside of z as well. Great. We can also talk about a set that has no elements at all, the empty set, and sometimes it will also be called the null set. Either way, it's a set that has nothing in it. It has no elements whatsoever. We represent it with this symbol right here, the empty set symbol. Now this set is going to be unique because any set that has no elements inside of it must be the empty set. There's only one empty set because there's only one way to have nothing inside of a set. So the empty set is just nothing at all. There's nothing inside of it. No elements, we've got the empty set. Since the empty set has nothing inside of it, it must inherently be inside of any other set. All of its elements show up in every other set, right? Each of its elements appear in every other set. Now, I've got the word trivially there because what it means is it's trivial. It's obvious in sort of a silly way. It's like, yeah, okay, sure, none of them show up, but yeah, of course nothing shows up because they don't have any there. But that doesn't make it not true. It's trivially true. It's kind of an obvious, silly thing, but it's still true. So that means, by our definition of subset, the empty set is a subset to everything. The set A equals walrus must have the empty set inside of it because that set has, in, a corner, nothing, right? Everything has a little nothing inside of it. B, 17, 27, 47, exact same thing. It's going to also have the empty set inside of it. A and B don't really have any connection other than the fact that they both have empty sets inside of them because any set at all, even the empty set itself, is going to contain the empty set. Because containing yourself is obvious because it just means you already have yourself there. All right, union and intersection. We can create new sets through having our sets interact with each other. So if we've got two or more sets, we can have an interaction between those sets and make another set. May or may not be different. The union of two sets is a set that contains the elements of each. We symbolize this with an open cup. So that gives us our union symbol. The intersection of two sets is a set that contains the elements and only those elements that are in both sets. So if an element shows up in both of the sets, it's going to be symbolized with the intersection symbol, sort of like a cup pointing down. So cup pointing up, we're filling it up with a bunch of things. Cup pointing down, it's cutting things off. We can also see this as a Venn diagram, right? Here we've got all the stuff in set A. Here we've got all the stuff in set B, right? So what they cover together, what they both cover here is A intersect B. The stuff that's in A and in B is A intersect B. The stuff that's in everything is going to be A union B. So we can see this with the idea of a Venn diagram as well. Union adds everything from all of our sets and makes a big set out of everything that we've got. And A intersect B is going to make a smaller set generally that's going to see where do you guys cut into each other? Where are you guys, where are you guys the exact same thing? And that's all we have left. Example using actual things, if A is equal to cat and mouse and B is equal to cat and dog, then A union B is cat shows up, mouse shows up, and then we go over to B, and cat, well, cat already showed up, so it's not that interesting to put it in again. We can't have copies show up in our set because everything has to be unique, but dog hasn't shown up before, so we get dog in there. Now for A intersect B, we ask, well, what's the thing that shows up in both of them? Cat? Cat, yeah, so cat showed up in both of them, so it gets to go here. But mouse doesn't show up over there. Dog doesn't show up in A, so it doesn't show up either. You have to be in both of the two sets, so intersection is if you are in both of them, you get to go on to the intersection. If you're only in one of them, not good enough. But union is you only have to be in one of them and you automatically make it in. You can be in both of them, and that's great. You still get in that way as well. Sets can be weird stuff. So we've talked about fairly simple stuff so far that it's been just like, finite, just a couple of elements at a time. And there've been some numbers, there've been some weird words, but we haven't encountered anything that crazy. Now, the sets you're going to see for math, at least for the next couple years, are going to generally just be sets of numbers. But as we've seen, we can also contain a lot of different ideas. We don't just have to be stuck with numbers. We can also have elements other than numbers, like words, or maybe even symbols or faces. We could have a bunch of different things inside of our set. The important thing is that they're distinct objects. We've also only talked about the idea of finite sets. So a finite set means that it has a limited number of elements. It doesn't just keep going forever. But we could also have an infinite set. That's going to be a set where the elements just keep going forever. So an infinite set means the elements keep going forever. We never stop. There's an unlimited number of elements. So how could we see an infinite set? Well, let's just start counting and never stop. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Right? There's no reason I have to stop. I'm going to stop because, I'm mortal and I'm not going to be able to count forever. But we get the idea that even though I can't count forever, even though there's no way to literally write an infinite number of things, it still exists as an idea. And so, as an idea, it's a perfectly fine set. So all of the numbers, just all of the counting numbers, just listed out forever and ever and ever and ever, that gives us a set. It's an infinite set because it has an unlimited number of elements, but it's a perfectly reasonable set. We can make even weirder, interesting, stranger infinite sets if we want. So consider the set where we take a word and then we repeat it an ever-increasing number of times. So word, and then word, word, and then word, 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 and then etc., etc., etc. So each time we do this, we'll make a new word, not really a word in English, but it's a word in our sense of making up a new thing. And if we keep doing this forever, we're going to have an infinite number of words. So for example, what if we took the word cat? Then we would have cat, 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 cat. I think I said cat 5 times. And we could keep going and going and going and going, right? This set has infinitely many distinct elements. No matter what number you say, there's an element in the set that's going to have that word cat repeated that many times. If you say 72, inside of this set right here, there is somewhere, not on this slide, but somewhere, if you just keep going, you're going to be able to imagine the idea of cat being repeated 72 times in a row. So we're creating new elements out of doing this. We build a set out of this idea, and each one of these is distinct from the others, right? Cat is not the same as cat cat, which is not the same as cat cat cat. So each one of these elements is distinct from the others, and there's an unlimited number of them. We've got an infinite set. So we can make really interesting, weird things in set theory. It's really, really cool stuff. We've just scratched the surface of how cool this stuff can get. I love set theory personally, but it's something you'll have to study in college if you're really, really interested in it. So I just want to finish off by saying sets can be strange and beautiful things, and there's a whole bunch of stuff out there. Now let's start talking about how all this set theory stuff applies to what we're going to be seeing in the near future in pre-calculus, and then hopefully one day in calculus. So we can talk about numbers as sets. So we understand the notion of a set now, and that's great. So we can now look at sets that make up numbers that we're going to use in math. So we've already seen one of the most essential sets. It was our first example of an infinite set. The natural numbers. N equals 1, 2, 3, 4, 5, 6, 7. So this is just starting at 1 and counting on forever. This is our first sort of most basic set in many ways, most basic infinite set, right? We get this idea of counting and never stopping from the age of like 3 on, if not maybe even earlier. We're getting this idea of you start counting and you just never stop. And of course, as a child, you realize, well, eventually I have to stop. I'll count to 100 and then I won't count any further. But you could just keep going. And that's the idea of the natural numbers, is you just keep going forever and ever and ever, and you've got an infinite number of elements. One thing to note is some teachers will define the natural numbers as starting with a 0. So you might instead have n be 0, 1, 2, 3, 4. So exact same thing on the latter part of it. The tail of it is going to look the same, but you might start with 0, you might start with 1. I prefer the version without 0 that instead starts with 1, but some teachers make a distinction and will call like the one starting with 1 the counting numbers and the one starting with 0 the natural numbers. The point is just pay attention to what your teacher is teaching you if you're taking an outside class, and make sure you're using their definition so that you get everything right on the homework and that you understand what they're trying to teach you. There's nothing better or, less good about one or the other. It's just sort of a taste thing, and I happen to prefer the version without 0. Also, I just really quickly want to talk about this symbol that we use. That is N in blackboard bold, which is to say what we would write out if we were writing the symbol by hand. However, it's kind of hard to make that symbol by hand since it's such a fancy typography symbol. Instead, if you were writing this out by hand, the symbol that you write is like this. So you start off with an N, and then you just drop another line down here, and that is seen as N if you want to write it by hand. Probably you're not going to have to write this stuff by hand for at least a while, and maybe not ever, but I want you to know in case you are interested in doing it. So let's keep expanding on these ideas. We can take the natural numbers and we can go, well, we've got positive numbers, but we've also got negative numbers. So let's count not just forward, but let's count backwards as well. So we'll hit 0 and then we'll just drive on into the negatives. This gives us the integers. So we start at 0 and then we go forward positive, but we also go backward negative. So 0, forward, 1, 2, 3, 4, 5, 6, 0, backward, negative 1, 2, 3, 4, 5, 6, 7, 8, sorry, negative 1, negative 2, negative 3. So we're going off both directions, and that gives us the integers. We use this symbol here with this special z. If you want to make this z, you start off with just a fairly normal z, and then you drop down this extra diagonal and join it with your z, and you've got the symbol for the integers in handwritten form. Now, I bet you're wondering, wait, so that made sense with the natural numbers. That was n, but why z? Z comes from German. I believe Zahlen is the word for integer. Maybe Zahlen is just numbers. And so Zahlen is numbers, and because German mathematicians were doing this work around the same time that English-speaking mathematicians were, and it was all being codified into symbols, we wound up using z for the German version of number because those mathematicians did a lot of great work when setting up set theory. All right, next idea, we can add yet another layer of depth by including the idea of division, right? So we've got 1, 2, 3, negative 1, 2, 3. These are great, and they get us a good idea of what's in the real world. But what if I want to talk about wanting half of a pie, right? Or if I want to talk about, well, he got $1.50, or something where I want to break a number into pieces. Now we have to be able to talk about fractions. And to do that, we use the rational numbers. So here we've got that interesting format where we've got the middle bar meaning where, such that, something like that. So what this means is we've got m over n, where m comes from the integers. M is one of these integers things. So it can be it can be a negative number, it can be a positive number, but it's going to be a whole number. And n is got to be contained in the natural numbers, which is good because we certainly don't want to be able to divide by 0, and because of my definition of the natural numbers, we're not allowed to have 0 in the naturals. So that means we can't divide by 0, so we're safe there. So this gives us the ability to have any number up top divided by any whole number that's positive on the bottom, which lets us make any fraction we want to, right? You give me any fraction, like say 47 over 9, and hey, look, we've got 47 belongs to the integers, 9 belongs to the natural numbers. If we want to talk about the fraction negative 52 over 101, well, we can turn that into being equivalent to negative 52 over 101, sorry, 101, not 100. And so we've got negative 52, well, he's an integer, and 101, well, he's a natural number. So right there, we've got the rational numbers. We're able to build out any fraction that we're used to seeing in normal circumstances. Any sort of normal fraction that we'd talk about, boom, we can make it now with the rational numbers. So this gives us a lot of ability to make numbers. We can get pretty much anywhere we want to be by using the rational numbers. Also, you might wonder, why is it q? Real quick, if we wanted to write this by hand, you make a q first, and then you drop a vertical line like that. So you've got q. That gives us our blackboard bold once again, which is just to say something we can write by hand that makes it other than just writing the letter q. So that lets us talk about that set of all the rational numbers. And why do we use the letter q? Because fraction is connected to the idea of quotients. So as opposed to using f, which we kind of use for functions a lot, as we'll talk about later, we use q to talk about quotients. So that's where we use the letter q from. All right, onward. We can also talk about rational numbers as a decimal expansion. We've got this idea of expanding a rational number into a decimal version. And there's nothing wrong with decimal versions, and we can have pretty much any number turn into a decimal version of itself. So the decimal expansion of every rational number, you probably learned this in grade school, every rational is either going to terminate, which means it ends, or it continues with repeating digits. So for our first example, something terminating, we have 0.09375 is what we get from 3 over 32, and see how it just ends right here. If we were to keep going, it would be 0, 0, 0, 0, 0, 0. We just have zeros forever, so we just sort of lop it off, and it terminates. It stops at a certain point. If, on the other hand, it continues with repeating digits, then that means there's some block of digits that will keep repeating forever. So 77 over 270, we get 0.2851, 851, 851. We realize 851, 851, 851. So 0.2, that happens first, and then a repeating block shows up 851, 851, 851, and it's just going to march 851 out forever and ever and ever. So if we've got a rational number, it's going to be one of these two things. It either terminates, it ends, or it repeats. So every rational number, anything that can be expressed as integer divided by integer, by whole numbers over whole numbers with maybe a positive or negative sign, that's going to have either the decimal ending or the decimal going forever but repeating. Why is this important? So this idea of the rational numbers is really great, but there's still some numbers we can't express. So you might remember that decimal expansions, if all the rationals either terminate or they go into repetition, there's at least one number you've heard of by now that keeps changing. Pi, right? You've learned about the number pi for probably quite a few years now, and you know that it just keeps shifting around, 3.1415, and you can memorize a bunch of digits if you want, but it's never going to just lock down and turn into something where you're done memorizing it. There's always going to be infinitely many more digits to remember. So pi never stops. It never repeats. It's not a rational number. You've probably also heard that root 2 is also not a rational number. These turn out to be true. We can't express them as rational numbers. We can't express them as a fraction of integers. The decimal expansion of an irrational number, unlike a rational, never stops and it always keeps changing. They're these sort of shifting, mixed up numbers that just always keep doing interesting things. They keep us on our toes, unlike the rational numbers. So if we want to really be able to describe everything that's out there, all of the numbers we might encounter, we need to be able to talk about the irrationals in addition to the rationals. Also, why do we call them irrationals? It's not because they're crazy and they're something weird. It's because they're just not rational. They are irrational. So irrational numbers just because they're not rational. Not because there's anything wrong with them, but just because they're not that set that we call the rationals. That's it. So if we want to put the rational and irrational numbers together to get something that we can really have all the numbers we'll work with, we've got a great set. That will give us the real numbers. So we put them together and we get the real numbers. These are our bread and butter in mathematics. You're going to be using them for years. You have been using them for pretty much everything you've ever done, unless you've worked on the complex numbers for a little while. And even if you did work on the complex numbers before, it was still using real numbers as part of those complex numbers. The only thing was that and it still had a real number right next to it. So real numbers make up pretty much a huge portion of mathematics. And unless you go for a whole bunch more math in college, which I would recommend, I really like math, you're not going to wind up seeing probably anything other than the real numbers until you get to some really abstract, interesting math. But it's going to take a while before you see anything other than the real. So they're a great thing to sort of make a home with and settle down with and get a good understanding of. And the purpose of all the set stuff beforehand is to be able to get a sense of, oh, how does this work? Where do the reals sort of live when we're not moving them around and working with them and doing things with them? We express them, if we want to be able to talk them with this nice simple symbol, we use R in this blackboard bold font. So if we want to be able to write this by hand, we make a normal R, and then we throw down this extra vertical line right here, and that's the symbol for the real numbers. And R stands for real numbers. Makes a lot of sense, unlike some of the other ones. If we want to talk about an interval of the real numbers, if we want to go into that sort of home of real numbers and say, well, I just want to talk about this one chunk, we can use interval notations. For example, we might want to talk about everything from -1 to 3. We don't want to talk about 100. We don't want to talk about -1 billion. We just want to talk about everything from -1 to 3, so we use interval notation. If we want to include the end numbers, we want to include -1 and 3, we use square brackets. So square brackets here give us inclusion. They keep those endpoints in it. So we'd go from -1 up until 3, and those points will be there. They are actually going to be part of our interval. -1 and 3, they show up. If we want to exclude them, we want everything in between them, but we don't want the end things, then we exclude them by using parentheses. So parentheses gives us exclusion. So that gets us -1 to 3, but without actually having -1 and 3. So -1 does not show up. 3 does not show up. So we use, if we want to symbolize it in a graphical manner as a picture, we use open circles like this right here to show exclusion. We use filled in dots to show inclusion. So exclusion with a parenthesis, a curved, empty circle, and inclusion with a filled in dot or a nice square, solid bracket. But in either case, -1 to 3 with square brackets, -1 to 3 with parentheses, we are going to always include everything between those. It's just a question of whether or not we're going to include the ends of the interval. If we want to talk about 4, 7, but we want to not include 4 and we want to include 7, we have parenthesis 4, 7 square bracket. So that's going to be all the real numbers between 4 and 7, of course, but it will keep the number 7 because we've got the square bracket, but it's going to not include 4 because we've got the parentheses. So the parentheses next to the 4 will exclude it, will keep it out, but the square bracket next to the 7 will keep it in. So we can talk about intervals where one end gets left out and one end gets kept in by mixing up how we use this interval notation. If we want to talk about the idea of infinity, then we can talk about going on forever. So infinity, the symbol for infinity, that nice infinity sign, This gives us a nice, convenient way to talk about going on forever. So if we want to talk about the interval going forever in one direction or the other, we'll use negative infinity or positive infinity. And keep in mind, when there's no symbol in front of it, we just assume that it's positive. So negative infinity has the negative sign, positive infinity doesn't have anything. If you absolutely had to symbolize that it was the positive version, you could put a little plus sign in front of it. So that will show us which direction we're going to go forever. Depending on the direction that we want to talk about going forever, we'll choose the appropriate infinity, negative or positive. Now keep in mind, you're always going to use parentheses with negative infinity or infinity. Why is it that we always use parentheses when we're talking about them in interval? It's because we can't actually include infinity. Infinity isn't a number, right? Infinity is just the idea of continuing forever. So since infinity is an idea of just keep going, it's not an actual place, so we can't end on it. To have a square bracket implies that we end on it and it's there. The parenthesis, on the other hand, will just show the idea of keep going, sort of keep reaching towards it. You'll never actually reach it, but the interval will just keep going towards that notion of infinity. So, for example, we could have negative infinity to 2 with a square bracket on the 2. That's going to be all numbers less than or equal to. Everything starting at negative infinity and working all the way up until 2, and we'll actually get to 2 and we will achieve 2. 3, infinity with parentheses on both of them is going to be all the numbers greater than 3, but we won't include 3 because we don't have a bracket on it. We've got a parenthesis on the 3, so it's going to be everything from 3, but not actually including 3. So we'll get really, really, really close to 3, but we'll never actually touch it. We'll never actually achieve 3. And finally, if we want to just talk about the entire real line, that's the same thing as saying negative infinity to positive infinity, because that's everything that the real numbers have. Start all the way from the very beginning, reach all the way to the beginning, and reach all the way to the end. Just keep reaching forever and ever. Go all the way to negative infinity, go all the way to positive infinity. That's going to be the same thing as just saying all the real numbers at once. All right, let's do some examples. So if we've got the set x equals ABC, the set y equals BCD, and the set z equals CDE, well, let's figure out a couple of different ways to talk about unions and intersections. So first off, x union y union z. So x union y union z, that's going to be equal to x union y is going to be all of the elements included in x and y. And then we union z on that, it's going to be in addition to all the units with z. So it's going to be all the elements that show up in all of them. A shows up, B shows up, C shows up. Well, B already showed up, C already showed up, but D is a new guy. C already showed up, D already showed up, but E is a new guy. So it's going to be A, B, C, D, and E. There we go. If we want to talk about x intersect y intersect z, then that's going to be what is the only place that they all have in common. What are the elements that is in each and every one of them? Well, A does not show up in Z, nor does it show up in Y. B does not show up in Z. It does show up in Y, but it has to show up in all three of them. C does show up in Y, does show up in Z, so C is in. And since everything else must not show up in X, it must be that the only thing inside of it is C. We can also break this down into two pieces. We can go, well, what is X intersect Y first? X intersect Y would be B and C, because those are the elements X and Y share in common. And then we intersect that with Z as well. The only thing that BC shares with Z is the C right here. So we get C is our answer to all of them intersecting. So if they're all unions and they're all intersections, it doesn't really matter the order that we choose, which ones to intersect, which ones to union first. It's going to be a question of how do they all interact? How are they, what if we put all of the elements and all of them together, or what element is inside of every single one of these sets. So it doesn't matter about the order there, it doesn't matter about how we approach doing it. But it does sometimes matter if we talk about intersection and union working together. So for example, if we had x intersect y, and then union z, well, we've got parentheses around it. While we haven't explicitly reminded you of the order of operations, I'm sure you remember that do stuff inside of parentheses first. So if x intersect y is inside of parentheses, then we have to do it first. So x intersect y, that spits out b, comma, c. And now we're going to union z. Z is going to be C, D, and E, so that gives us a total of B, C, D, and E in our set. So B, C, D, E. But compare, what if we did it a different way? If we had X being unioned with the intersection of Y and Z. Now we need to start off by asking, well, what is the intersection of y and z? Well, C and D show up in both of them. E does not show up, B does not show up in both of them. So C and D makes up the intersection of y and z. So X union C comma D is going to be A and B, because they're new guys, and C and D were already there. So A, B, C, D is X union Y intersect Z, but we get a different one if we do X intersect Y union Z. We get B, C, D, E. So notice, these two things are not the same. There's not an equivalence between those two sets. They're not equal sets. So they aren't the same set because how we approach putting these things together matters. It's not like 3 times 4 times 5 is the exact same thing as 4 times 3 times 5 is the exact same thing as 5 times 4 times 3. It matters how we put these together because we've got different things going on. It's not just multiplication in a way, it's multiplication and addition. It matters the order that we do it in. So intersection and union, we can't just do it in any order. We have to pay attention to the order that it's been put together in. Next example, we've got N, Z, Q, and R. We've got all those big number sets that we talked about before. Which one of them will be subsets to the others? How will the subsets work? Well, first off, let's start off with reminding ourselves about what these are. N is everything from, not 0. I don't believe in that one. Set that one wrong. 1, 2, 3, 4, ... Just keep going forever. The integers are going to be going off in the negative direction and the positive direction. So we've got ... up until, and then we sort of meet up, and then we just keep going that way. And if we talk about the rationals, that's the way of saying all integer fractions. Fractions made up with integers on the top and bottom. So that's going to give us the rationals. And the reals are just all numbers. What we're used to is thinking of all the possible numbers. So all numbers are the reals. Well, with that in mind, it's pretty easy to see that the natural numbers, well, since the integers, not equal, subset is what I meant to write. Since the natural numbers are 1, 2, 3, 4, they're all the positive integers, well, they must show up in the integers because the integers are the positive integers and the negative integers and 0. So N is a subset of Z. Now, Z shows up in the rationals. How is that possible? Well, if you give me any integer number, I can very easily make a rational number out of it, right? If you give me -5, well, -5 over 1, that's the same thing as -5, and -5 over 1 is very clearly contained inside of the rationals. -5 over 1 is very clearly an element of the rationals. You give me any integers, like -572, then I just put it over 1, and once again, we're back inside of the rationals. So whatever integer you give me, pretty clearly, it's got a rational version as well. We can keep going and now include the reals. We can talk about the reals, and the reals are going to have everything because we define the reals as having all of the rationals and all of the irrationals, so the rationals fit inside of the reals as well. So we've got subsets going up of N is a subset of Z is a subset of Q is a subset of R. That also means that because this stuff was transitive, N is also a subset of Q, and N is also a subset of R. Z is also a subset of R as well, and those are all of the relations that we can get out of this. N is a subset in Z, is a subset in Q, is a subset inside of R. Cool. Third example, if we let A be the set of all titles of all published written works, and B is all of the phrases that are precisely 3 words long, let's talk about what would be some elements inside of A intersect B. Now, to start off with, there's not just a couple of answers to this. There's not just one finished answer. There is way more answers than I am aware of. But I can give you some examples and talk about how to think about this. So let's also just rephrase this. We have another way of thinking it. A is the same thing as talking about A is everything. A is every title of books and magazines and poems. It's everything that is a written piece of work that has been published, that we could have actually gone to a store and bought or found in a published form. So A is every title of books and et cetera, et cetera, et cetera. Everything written that is published, that is what A makes up. Now B is something, well, everything from the way we're writing this. So B is everything that is 3 words long. So B is everything 3 words long. So what we're looking for, if we want to find intersection of A and B, then A intersect B is going to be things that are in both. So if you are in both, then to be inside of A intersect B, that's the same thing as saying titles that are 3 words long. So A intersect B is just titles that are 3 words long. So to be able to answer this question, we just need to figure out what are some titles that are 3 words. So we start thinking, and here's some of the ones that I thought of. We could go, oh, Romeo and Juliet, right? Almost everyone is going to know Romeo and Juliet, so that's a good one to start with. Romeo and Juliet, right? There is a title that is 3 words long, written by Shakespeare, and it is a published piece of work. We've all been able to find a copy of Romeo and Juliet if we've been looking for it. So Romeo and Juliet, that's one. What about another one? How about Things Fall Apart by Chinua Achebe? Things Fall Apart. Or we could also talk about something by Kurt Vonnegut. Kurt Vonnegut wrote Breakfast of Champions. So Breakfast of Champions is another example of something where we've got a word that is 3 words long, a phrase that is 3 words long and is the title of something that is a written work. We'd also talk about To the Lighthouse by Virginia Woolf. So To the Lighthouse is another example. So there's a whole bunch of examples out there, right? I can't list all of these because we'd be here for days and days and days and days, and heck, I don't know them. But it's going to be anything that is written and has 3 words in it. So 3 words, not just in it, but 3 words for the title, precisely 3 words. So as much as I'd like to be able to say, you know, Cannery Row, or Of Mice and Men, or 1984, I can't talk about those because they aren't precisely 3 words long. So there's a lot of books out there that aren't 3 words long in the title, and there's lots of phrases that are 3 words long, like hot in here. Sorry, didn't come up with any brilliant phrases in that period of time. But any phrase that's 3 words long would be in B, and any title would be in A, but what we're looking for is the intersection of A and B, so titles that are 3 words. So Romeo and Juliet, Things Fall Apart, Breakfast of Champions, To the Lighthouse. These are all some examples from various different authors. Right. Final example, example 4, list all the subsets of x, y, z. Very first subset that we have to remember is the empty set. So the empty set shows up as a subset for everybody. So the empty set is our very first subset. Next one, well, let's look at all of the subsets that have 1 element inside of it. So x, whoops, I made a really bad bracket there. X is going to be a set just on its own, and that's a subset. Another one would be y. That's another subset. Another one would be z. So those are all of the sets that are 1 element long and are subsets of x, y, z. Now we can go with the 2 element ones and we can say, all right, well, x comma y, that's going to be a subset. What about x comma z? And then finally, y comma z. And we think about that for a little while and we realize, yep, those are all the sets I can possibly make out of x, y, z that have 2 elements precisely in them. X and y, x and z, y and z. You could rearrange them in different orders, but remember, since it's a set we're talking about, order isn't important. It doesn't matter the order that it shows up, just that it did show up at all. So those are all of the sets that are going to be 2 elements long and are subsets of x, y, z. And then finally, we've got x, y, z itself is a subset of itself. Because remember, by the formal definition of being a subset, it just means that all of the elements inside of your set show up in the other set. And every element x, y, z shows up inside of x, y, z. Makes sense. So every set is a subset of itself. kind of obvious and not that really, interesting. So it's another trivial assertion. It's interesting to think about, but not something that really gains us a lot of knowledge for any specific thing. But it's still an interesting idea and might have other connections later on if we think about it a lot. All right, so that gives us a total of 8 subsets, and those are all of them. All right. I hope you enjoyed this. I hope you learned some stuff about sets. Like I said before, we're not going to really focus on the ideas that we had here, but what we just did was we built a foundation of pretty much everything else that you're going to wind up ever seeing in math. Virtually all of modern mathematics is built upon the idea of set theory. It can be explained through the idea of set theory. So I just wanted you to get some exposure to this foundation so that later stuff we talk about, like when we talk about functions and a whole bunch of things, in fact, we've got some idea of being able to refer back to these sets, pulling things out from sets, going to other sets. Really cool stuff here. Set theory is really fascinating. I totally recommend studying it sometime if you get the chance. But I'm glad that you managed to get here and that you've got some idea of how sets work. And we'll see you in the next lesson. Bye. Talk to you later at educator.com.